students. My name is Dr. B. Suresh Babu, working as a professor in the Mechanical Engineering Department, 1 year College of Engineering and Technology, Paritala. As a part of online classes, today's presentation is on material behavior. If you observe the screen, you can see the fourth unit syllabus in advanced materials. In this one, in the previous class, a part of introduction is given for presentation to you. On 6th also, a presentation is given in single class. In continuation of the first class, second class is also covering the introduction and 6th concepts only. If you observe introduction, in the previous class, introduction is about what are the stresses that are going to act on a member or an object or any lamina. Then how the material is going to behave, we have studied. Symbolically it is represented. At the same time, with the help of graph also I have represented or I have explained to you to understand in a better manner. In the previous concept, we have studied about the sixth law, studied about types of stresses, and studied about the what is a lamina and what is a mechanical behavior and how macro mechanical properties or macro mechanical behavior of a lamina will be when a forces are going to act on a lamina. That is the thing we have explained. I have explained and we have learned. I repeat once again, if the previous class summary is observed, I have defined what is the stress, what is strain, and how these two are related with Uppsala. And another concept is what is a lamina and what is macro mechanical behavior of a object. In this class, the concentration is on materials, material properties, and how Uppsala is connected to these material properties. So this is the main theme of this class. I repeat once again, the theme of the class is what are the properties of a material and what are the materials that are there and how these material properties are related to this Uppsala. So these three concepts are we are going to broadly explain, and in a minute manner we have number of points can be discussed while explanation is going on. Try to pay attention, students. Let us go for materials. So materials are broadly classified into two types. One is going to be called as a ductile material and another one is going to be called as a brittle material. Try to understand, students, in mechanical aspects, these two are going to primary classifications. One is called as a ductile material and second one is going to be called as a brittle material. So what is a ductile material? A material that is going to be failed or lost its function by giving a warning before it is going to fail is going to be called as a ductile material. That means a material that is going to give warning before it is going to be fail. Its function is going to be called as a ductile material. Then what are called brittle materials? A material that is going to be failed suddenly without giving any warning. Then the type of materials are called as a brittle materials. These are broadly we can define the definition of these two. Once again, if you observe the ductile material, how the ductile material can be scaled? Ductile material can be scaled in two types. One is going to be while giving the warning can be in the form of a wire or in the form of a small diameter. Second type of material is, or second type of classification is, if that is going to be sold in the form of a very thin sheet, then that is going to be called as a malleability. So ductility and malleability are the two properties of a material in a ductile material. That means ductility means if a ductile material can be drawn in the form of a wire, then the type of material is going to be called as a ductile material, and the property is going to be called as a ductility. That's the first point to remember. At the same time, same ductile material of nature or the type of category, that material can be elongated in the form of a sheet. Then the type of nature is going to be called as a malleability of the material. That means broadly, a material that can be drawn in the form of a wire is called ductility property, and a material that can be drawn in the form of a sheet is going to be called as a malleability property. So this is the two things which can classify this one. Here if you observe this one example, so materials that are generally described as ductility include gold and copper. Malleability, a similar mechanical property, is characterized by a material's ability to deform plastically without failure under compressive stresses. So that means what is the plastically means? It can be drawn in the form of a sheet. Here a lead is an example, if you observe, which is relatively malleable but not ductile. That means lead can be drawn in the form of sheets, but that cannot be drawn in the form of wires. That is a lead. If you take gold and copper, gold wires will be there, gold sheets will be there, copper foil will be there, copper sheets will be there. But in case copper and gold can be used for ductility material as well as malleability material. That's things we have to observe here. Next, brittle materials. Brittle materials include glass, ceramics, graphite, and some alloys with extremely low plasticity in which cracks can initiate without plastic deformation and can soon evolve into brittle breakage. What the meaning is, we have given certain examples. When a load is applied on a brittle material, the material does not sag or does not elongate or does not deform by the application of load. And at the same time, it will generate cracks at the point of load. And extreme edges, that cracks are going to be expanded. Due to this one, material will going to be broken into number of parts. Like this, if a material is going to give feedback on the load applied point, then those materials are going to be called as a brittle materials. So a material does not expand or elongate or not deform when load is applied, then the type of materials are going to be called as a brittle materials. For example, they observe the same means glass, ceramics, graphite, all materials are the type of nature only. And if you observe cast iron, also similarly it will behave. So if a large load is applied, cast iron cannot able to deform or cannot sag. So this is the thing to be observed. So this is the main from this slide. What we can observe is students have we have learned what is ductility nature, what is malleability nature, and what is brittle type of nature. and what are called ductile type of materials. So these are the four things we have learned from this slide. Next, in connection with this ductility and malleability, if this expansion or deformation is done in terms of volume, if you calculate in terms of volume, then that can be defined with the help of a bulk modulus. So what is the bulk modulus? It is a volumetric factor to explain the expansion and deformation of a material. So I will read out the definition of this bulk modulus. A bulk modulus is a constant that describes how resistant a substance is to compression. That means it is defined as the ratio between the pressure increase and resulting decrease in the material volume. So that is the theme you can able to understand what is the theme behind this definition. That means if the pressure is applied, then material is going to be resulting in decrease in material volume, then that is going to be called as the bulk modulus. So bulk modulus is a constant that describes how resistant a substance is to compression. That means when a metal is going to be compressed, how far it is going to be resisting is going to be called as a bulk modulus. So bulk modulus means a bulk modulus of a substance measures the substance resistance to uniform compression. That means a property of a material that can be measured how much is resisting when a compression force is applied. For example, rubber is there. Rubber we are going to compress means it can be compressed. If you take this pen cannot be compressed because it has not that type of nature. So bulk modulus, if you take a metal, bulk modulus does not compress. That means the metal is compressed, bulk modulus cannot be very good. If you take a rubber, it can able to compress. That means resistance is going to be very low. So bulk modulus is high for a steel material or a metal and is low for a rubber. That thing you can observe. So it is defined as the ratio of infinitesimal pressure increase to a resulting relative decrease of the volume. Its SI unit is particle. So this is how we can define. So bulk modulus is denoted by the letter K. It is as we are decreasing the volume, that's why minus Vd by Vdp. So that is the concept of this bulk modulus. So what is this screen says or this slide says is about the bulk modulus. How you can define the bulk modulus? How much pressure you have applied and how much it is resistant for this decrease in volume is going to be called as the bulk modulus. It is the ratio of pressure increase to the resulting decrease in the material volume is going to be called as the bulk modulus. It is one of the parameter of the material to understand the property of deformation. Next, another type of material is called and property is called Young's modulus. So what is the Young's modulus? It is defined as the ratio of the stress applied to the material along the longitudinal axis of the specimen surface and the deformation or strain measured on the same axis. So if you observe this one, the material is there. On this metal, stress is going to be applied on the longitudinal member like this. Then it is going to be the expanded. That means the strain, that means change in volume takes place. How much change in volume takes place? That is the measure for defining the Young's modulus. So Young's modulus is also be called with a similar name, other synonyms. That is tensile modulus, elastic modulus, or modulus of elasticity. So Young's modulus is also known as the tensile modulus, elastic modulus, and the modulus of elasticity. So when this happens, When we are going to apply the force on a material on a longitudinal direction. So we are going to apply the stress. With that stress, how much it is expanding, we have to calculate. By that one, we can able to calculate this Young's modulus. It is noted by the letter E. Next, when a stretching force, that is tensile force, is applied to an object, it extends and its behavior can be obtained using stress strain curve in the elastic deformation region known as the Hooke's law. When a stretching force, that is tensile force, is applied to an object, it extends and this behavior can be obtained using stress strain curve in the elastic deformation region. So what we are explaining is as a beginning of the class we have I told the class is connecting with knowing about the types of materials, metal properties, and introduction of this continuation of the Hooke's law. What the Hooke's law says, within the elastic limit, stress is directly proportional to the strain. If you observe this one, the same concept, the extension that a force produces is not only depend on the material, but also on other factors like dimensions of the object. It is not purely depend upon the force what we are going to apply, but also it includes the other factors like dimensions like length, thickness, width. They have interrelated to this one. So Hooke's law is within elastic limit, stress is directly proportional to strain. Next, the greater the value of Young's modulus means, the greater the stiffness of the material. What is the stiffness? The ability of the material to resist deformation is going to be called as a stiffness. For example, if you take this pen, so try to expand like this, it is going to resist. If the same is done for a rubber, it will expand. That means stiffness for the rubber is low when compared to this pen. That means if it is higher Young's modulus means it has more stiffness. So that is the thing you can understand from this statement. Next, unit of Young's modulus of elasticity. Young's modulus or modulus of elasticity is Newton per meter square or Pascal. The unit is Newton per meter square or Pascal is the unit. So what is the important thing you observe from this one is definition of Young's modulus, nature of the Young's modulus with respect to stiffness, and unit of Young's modulus, and letter to denote the Young's modulus. So these three you have observed. Young's modulus, it is a ratio of stress applied to the material along the longitudinal axis of the specimen tested in the tested along the direction of the axis. So this is the two things you learned here. One is about the Young's modulus, second one is about the bulk modulus. Before that one, we have learned about the stress and we have learned about the ductile material and brittle material. Stress and strain are going to become now. So already I explained the little part of the stress. What is the stress is equal to force by area. What is the meaning of force by area? If a large area is there and small force is applied. So force by area, if you take the ratio like this, the stress is going to be very, very low. If a small area is there and force is applied, and same force is applied, then stress is going to be very high. So it depends upon the force and the area. Stress is equal to force by cross-sectional area, that is P by A. So what is the stress? So when a body is subject to extreme forces, equal and oppository forces are developed at the various sections of the body. Resisting force is known as a stress. The stress is generated written by the Greek letter, that is sigma. In a system of international SI units, it is Pascal. 1 Pascal is equal to 1 Newton per square meter. In practical calculation, if stress is very high, the unit can be written as megapascal or we can written as a gigapascal. So this is about the stress. Next we will go for the strain. What is the strain? Change in length by original length is going to be called as a strain. When strain happens, when object is externally loaded, due to that load, metal try to deform. If the deformation is in one direction only, then it latest is Young's modulus of the material. If the deformation is in volumetric, that means throughout the surface of the object, then we are going to call it as a bulk modulus. If Young's modulus is high, means the stiffness of the metal is very high. If Young's modulus is low, means stiffness of the metal is going to be low. Similarly, for bulk modulus, how we can explain? While applying the load means when a pressure is applied, deformation is very small. That means reduction is small means we are can expect bulk modulus is going to be very high. For the same application of the load, if the deformation of the surface is throughout, then we can say that it is going to be a more deformation means less bulk modulus. Less deformation means more bulk modulus. So like this, you can remember this Young's modulus and bulk modulus. Coming to how these two related to the ductile material and the brittle material. Young's modulus, if you take Young's modulus will be very high for a brittle material. Young's modulus is low for a ductile material when compared with the brittle and this ductile. Similarly, bulk modulus. If bulk modulus is very low for a ductile material and bulk modulus is very high for a brittle material. So like this, you can able to understand this. So this is how we can explain the stress strain concept with the ductile material and brittle material. At the same time, the same concept can be explained for the Young's modulus and the bulk modulus. Next, what are the applications of this one? This elastic modulus or a bulk modulus. Elastic modulus is an important mechanical property for a material selection. For material selection, Young's modulus is also one of the important factors. Why? Because you have to consider expansion, thickness also. Along with that one, we can go for a product design and performance analysis in several engineering as well as medical applications. So in engineering applications as well as medical applications also, Young's modulus is going to be considered. And at the same time, for a material, we analyze its function. Then also, important property is Young's modulus. That is, for the performance of a material to test it, we are going to consider this elastic modulus as one of the properties. Next one. What are the things we can use? These are used for selection of materials for various purposes, considering how it will react under different types of forces to aid design process, to reduce material cost, determine batch quality and consistency in manufacturing. So these elastic modulus or metal behavior or property. It counts also what type of material, at the same time how much it is going to be reduce the cost if you use this material, and that quality of the material also can be different from this one, and consistency in the manufacturing process is also, and the product quality is also depend upon the material nature only. In this material nature, elastic modulus is going to be play a prominent role. That is the thing. So from this slide, what you have understand, what are the applications of elastic modulus? It includes cost of the material to be seen, quality of the material or product, and consistency in manufacturing process, medical applications, engineering applications, in product design, and cost of the material. So these are the six factors that can be influencing the material and that material can be prominently decided based upon one of the property that is called elastic modulus. Next, what are the factors affecting this elastic modulus? The modulus is correlated to binding energies of the atoms. So binding forces means and the modulus of elasticity are typically higher for high melting point materials. That indicates what? If modulus of elasticity is more, then Young's modulus is going to be more. So Young's modulus is also be called as a modulus of elasticity. So modulus of elasticity is more means it has a more melting point. That we can remember. At the same time, Young's modulus also depends upon the orientation of the atoms and molecules. For example, if pen is there, if molecules are orderly arranged in one direction only, in the same direction we can able to separate the materials. That means it can able to break like this. If you take a material can able to resist in one direction to a strong extent, to a large extent. And the same material can be broken into pieces in other direction. Why? Because it purely depends upon the orientation of the molecule. So what you understand? So factor of acceptance modulus is orientation of the molecule and depends upon the melting point of the material. Next, higher temperature. If the metal increases with the temperature, definitely atomic vibrations atoms are going to move from one place to another place. It in turn affects the property of a material. But in case if stress is applied, it can able to be deformed. So by the application of temperature, the stresses can be easily be applied on that one and deformation can increase. If deformation increases means it is directly affecting Young's modulus of a material. That's why Young's modulus of a material depends upon the temperature also. That's the second point to remember. Third point is Young's modulus will also depend upon the property of the material, or we can say about the impurities present in the material. What type of impurities means? The impurities if you observe this slide, it may be a dislocation of the atoms, overlapping of the atoms, or mixing of the atoms, or changing the position of the atoms. These are all some kind of impurities of the atoms. So in presence of impurity atoms, alloying atoms, non-metallic inclusions, dislocations or mismatches in the lattice structure, defects, cracks, grain boundaries, etc. All of this can form the one of the nature that is called Young's modulus of the material. So it depends upon. So from this slide, we have observed 3 points. One is going to be the Young's modulus will depend upon the orientation of the atom, temperature of the material or external factors, and impurities present in this atom. So if you observe, this is the stress symbol. Two P's are applied on a yellow object, and these are going to be in opposite to each other. That is the thing to be understand here. So this is going to be called as a tensile stress, and another one is going to be called as a compressive stress. So tensile stress is nothing but TRS are opposite to each other, away from each other. Here in compressive forces, two are acting one against each other. So it is represented by the letter sigma. If you observe this behavior of a material, particularly, I already have explained this one, stress versus strain. A, B, C, D are the 5 points we have mentioned. At A point, if you remove the load, material does not change its shape or size. At the B point, if you remove also, the same thing happens. And that up to B to A is going to be called elastic behavior. That means number of times also up to adding load also it does not change, it does not lose its nature. At C, after B, if you applied again load, it reaches to C. And if you remove the load, there is a small change in the orientation or dimensions of the object. Then that type is going to be called as a yielding point, and the point is going to yielding point. Beyond the yielding point, if you apply the load, then that leads to the plastic behavior of a material. What is the plastic behavior? After C, if you remove the load also, the material tries to expand until up to D. At the D point, if you remove the load, it does not, it will try to expand continuously. At the D, if you remove, that will try to come to E and try to take a failure of that one. And this type of failure is going to be called as a ductile failure. For ductile material, this type of failure will happen. For brittle material, at ultimate load only it is going to fail. That is the thing we can observe from this graph. So 6 kilometers plus phases, stress is directly proportional to strain, and already stress is the force on unit area in the material that develops the result of the extremely applied force. Strain is the relative deformation produced by stresses. For relatively small stresses, and is proportional to strain. So sixth law, already this equation I have explained here in the previous one, the same thing I have explained here also. F is equal to minus kx. In this equation, F is the force, x is the extension length, k is the constant of proportionality known as the spring constant, that is Newton per meter. When elastic matrix are stretched, the atoms and molecules also try to expand. Then only the material tries to take deformation. And when stress is removed, it once again is back to initial material. So if you observe the previous graph, A up to B, it is elastic nature. Beyond B means material lost its nature. That is the point to remember, students. If you observe this graph, the steel we have high modulus of elasticity when compared to the biological tissues or rubber or plastic. So sigma is equal to E by epsilon. Epsilon means strain. Sigma means stress. Capital E means Young's modulus of material or modulus of elasticity or elastic modulus. That's the synonyms for this one. So we have a complete noting available in a 4 to 5 days for this unit. If you have any doubts, you can mail me to the mail ID cheer5@redismail.com. All of you register for Google Classroom course where complete notes is available with syllabus and important questions and topic-wise notes. By this, I am going to close, students, for today's session. Thank you. Have a good day. See you all. Bye, students.